You know, people ask me all the time, why can't I walk through walls? It seems like such a stupid question at first, doesn't it? I mean, you look at a wall, it's solid, you're solid. Of course you can't walk through it. But wait a minute. Think about what you learned in school. They told you that atoms are mostly empty space, right? They showed you those pictures with a tiny nucleus in the center and electrons whizzing around way out there. And all that space in between is just, well, nothing. So if you're made of atoms that are mostly empty space and the wall is made of atoms that are mostly empty space, why the hell can't you just pass right through like one cloud passing through another cloud? That's the real question. And the real answer, is so beautiful and so strange that it's going to completely change the way you think about what it means for something to be solid. Because I'm going to tell you right now, solidity, the thing you feel when you touch a table or lean against a wall, has almost nothing to do with stuff bumping into other stuff the way you think it does. Let me start with what you think is happening. You probably imagine that when you push on a wall, the atoms in your hand are getting close to the atoms in the wall, and then they touch, and they can't get any closer because, well, they're solid little balls, and solid things can't pass through each other. But that's completely wrong. Atoms are not little solid balls, not even close. Let's think about what an atom really is. You've got a nucleus in the middle made of protons and neutrons, and that nucleus is incredibly tiny. If you blew up an atom to be the size of a football stadium, the nucleus would be like a little pea sitting right in the center. And the electrons, they're even smaller. They're out there somewhere in the stands. But here's the thing, they're not really out there as little dots. They're kind of smeared out in what we call a probability cloud. You can't say the electron is right here at this spot. You can only say there's a certain probability of finding it in this region or that region. So when you add it all up, the atom is this bizarre thing where almost all the mass is concentrated in this ridiculously tiny nucleus. And then there's this fuzzy cloud of electron probability spreading out over a region that's 10,000 times bigger. Everything in between is just empty space. No stuff there at all. Now, if that's true, and it is true, we've measured it, we know it, why can't your hand, which is a bunch of these mostly empty atoms, just slip right through the wall, which is also a bunch of mostly empty atoms? It's like asking, why can't you walk through a chain link fence when most of it is holes? Well, okay, bad analogy, because you actually can't walk through a chain link fence because you'll hit the metal. But imagine the fence was made of fog, little wisps of fog, with huge gaps between them. You should be able to walk right through. But you can't, and the reason you can't has nothing, and I mean nothing, to do with the atoms physically bumping into each other like billiard balls. The real reason is electric forces. See, the electrons in your hand, they're all negatively charged, and the electrons in the wall, they're all negatively charged too. And here's a basic fact about electric charges. Like charges repel. Put two negative charges near each other and they push apart. Put two positive charges near each other and they push apart. It's one of the fundamental rules of nature. So when you bring your hand close to a wall, before anything touches anything, before any of this so-called contact happens, the electrons in your hand and the electrons in the wall start pushing on each other. They repel. And this repulsion, this electric force, it gets stronger and stronger the closer you try to get. It goes like 1 over the distance squared. So if you cut the distance in half, the force gets 4 times stronger. If you cut it in half again, it gets 16 times stronger. It grows fast. Now you might think, okay, so the electrons repel, but what about the nucleus? The nucleus is positively charged, right? Because it's got protons in it. So maybe the electrons in my hand are attracted to the protons in the wall, and that balances things out. Well, yes and no. The electrons are attracted to the nuclei, that's true. That's actually what holds atoms together in the first place. The electrons are attracted to their own nucleus, and that's why they don't just fly away. But here's the thing, in a normal piece of matter, in a wall or in your hand, the number of electrons exactly equals the number of protons. Every atom is electrically neutral overall. So when you look at the big picture, when you're pushing your hand against the wall, the repulsion between the electrons in your hand and the electrons in the wall is what dominates. The attractions to the nuclei are there, but they don't let you pass through. They just hold the atoms together. And the force is strong. I mean, really strong. You think you're pushing hard on the wall, but the wall is pushing back on you with this enormous electric force. Every electron in the surface atoms of your hand is being repelled by every electron in the surface atoms of the wall. And when you add all that up, it's a huge force. That's what you feel. That's what solid means. But wait, there's more, because even if we just had electric forces, you might think, okay, well, can I push really hard? Can I just overcome that repulsion and shove my atoms through the wall's atoms? I mean, the repulsion gets stronger when you get closer, but maybe if I push hard enough, I can force my way through. And the answer is no, you can't. And this is where it gets really quantum mechanical, really weird. There's another principle at play, and it's called the Pauli Exclusion Principle. Now, this is one of the most important rules in all of quantum mechanics, and it's the reason matter takes up space. It's the reason you can't compress stuff down to nothing. Here's what it says. Electrons are what we call fermions. Fermions are particles that have a property called spin 1/2. Don't ask me what spin really is. It's a quantum thing. It doesn't mean they're literally spinning like a top, but they have this property. And the rule for fermions is that no two of them can be in the exact same quantum state at the same time. They can't have the same position, the same energy, the same spin all at once. They have to be different somehow. This is completely different from particles like photons, which are bosons. Bosons love to be in the same state. You can pile as many photons as you want into the same quantum state, and that's actually what a laser is. It's a whole bunch of photons all doing the exact same thing. But electrons, they can't do that. They're antisocial. They refuse to occupy the same state. Now, what does this have to do with walking through walls? Well, think about the electrons in your hand and the electrons in the wall. Each electron is in some quantum state, some particular configuration of where it is and what it's doing. When you try to push your hand into the wall, you're trying to force the electrons in your hand into the same region of space as the electrons in the wall. You're trying to make them overlap. But they can't overlap. Not completely, because that would mean they're in the same quantum state, and the Pauli Exclusion Principle says no, you can't do that. So the electrons resist. They push back, not just because of the electric force, but because of this fundamental quantum rule. It's like there's an extra force, a quantum force, that prevents them from being in the same place, and this is what gives matter its solidity. This is why you can't squeeze a rock down to the size of a pea. This is why white dwarf stars, which are the dense remnants of dead stars, don't collapse under their own gravity even though they're incredibly heavy. The electrons in the white dwarf are packed so close together that they're all in different quantum states, and the Pauli Exclusion Principle creates this outward pressure, this degeneracy pressure, that holds the star up. Without the Pauli Principle, the star would collapse. So when you lean against a wall, you're not really feeling the wall in the way you think you are. You're feeling the electric repulsion between electrons, and you're feeling the quantum mechanical resistance that comes from the Pauli Exclusion Principle. It's not about stuff bumping into stuff. It's about fields and forces and quantum rules. Now let me make this even stranger. I told you that atoms are mostly empty space, and that's true. I told you that the forces keeping you from walking through a wall are electric and quantum mechanical, and that's true too. But here's something that will really bake your noodle. Even the particles themselves, the electrons and protons and neutrons, even they are not really solid little balls. They're not things in the way you think of things. In quantum mechanics, particles are described by wave functions. A wave function is a mathematical object that tells you the probability of finding a particle at different places. The particle doesn't have a definite position until you measure it. Before you measure it, it's kind of spread out, existing in a superposition of many possible locations at once. It's a wave of probability, and when you have a lot of particles together, like in your hand or in a wall, they're all described by this incredibly complicated wave function that includes all the particles and all their interactions. The whole system is one big quantum wave, and when your hand gets close to the wall, these two quantum waves interact. The interaction is governed by the Schrödinger equation, which tells you how wave functions evolve over time. What the equation says when you work it all out is that the probability of your hand passing through the wall is not zero. It's not impossible. It's just incredibly, incredibly, incredibly unlikely. There's a tiny chance that all the particles in your hand could quantum mechanically tunnel through the wall, just appear on the other side without ever having enough energy to climb over the barrier. Quantum tunneling is a real thing. It happens all the time in small systems. Electrons can tunnel through barriers that they shouldn't be able to cross. That's how some kinds of microscopes work, and it's how radioactive decay works. A particle inside a nucleus doesn't have enough energy to escape, but every once in a while, it tunnels out. But for something as big as your hand, with something like 10 to the 27th atoms, all of them would have to tunnel at the same time, in the same direction, for you to pass through the wall. The probability of that is so small that if you stood there, pushing on the wall for the entire age of the universe, and I mean the age of all possible universes, it would still never happen. The number is something like 10 to the minus 10 to the 50th. It's zero for all practical purposes. So technically, quantum mechanically, there is a wave function component where you are on the other side of the wall. But it's so unimaginably small that it doesn't matter. The universe doesn't work that way on our scale. But here's what I want you to take away from all this. The reason you can't walk through walls is not because matter is made of hard, solid stuff. It's because of forces and quantum rules. It's because electrons repel each other. It's because fermions obey the Pauli Exclusion Principle. It's because the quantum mechanical wave function for your hand, and the wall doesn't have any significant amplitude for configurations where they overlap. Solidity is an illusion in a sense. It's an emergent property that comes from these deeper rules. When you touch something, you're not really touching it. Your electrons and its electrons are repelling each other at a distance. There's always a tiny gap, a tiny space between them. You never actually make contact in the way you think you do. And this is true for everything. When you sit in a chair, you're not really sitting on it. You're hovering just above it, held up by electric forces. When you walk on the ground, you're not really touching the ground. Your feet are being pushed up by the electrons in the ground, repelling the electrons in your feet. It's all forces. It's all fields. There's no touching. Now, you might say, okay, fine, but that's just semantics. Whether I call it touching or I call it electric repulsion, I still can't walk through the wall. So what's the difference? And you're right in a practical sense. The phenomenon is the same. But understanding the real reason, understanding that it's about charges and quantum mechanics and wave functions that changes everything. It opens up the whole world of how matter really works. Because once you understand this, you can start to ask other questions. You can ask, why do some materials conduct electricity while others don't? And the answer has to do with whether the electrons are free to move or whether they're bound to atoms. You can ask, why is diamond so hard while graphite is so soft, even though they're both made of carbon? And the answer has to do with how the carbon atoms are bonded together, which comes down to the quantum mechanical arrangement of electrons. You can ask, what happens inside a neutron star, where matter is compressed so much that the electrons are forced to combine with protons to make neutrons? And the answer is that the Pauli Exclusion Principle still applies, but now it's the neutrons that can't be in the same state, and that creates an even stronger degeneracy pressure. You can ask, what is a superconductor where electricity flows with no resistance? And the answer is that the electrons pair up in a special way that lets them act like bosons instead of fermions, so they can all drop into the same quantum state and move together without scattering. All of this comes from understanding that matter is not stuff. It's patterns of quantum fields governed by forces and symmetries and principles, like the Pauli exclusion rule. Once you see that, you see the universe differently. And here's the kicker. Even the forces themselves, even the electric force that's pushing your hand away from the wall, even that is not really a force in the classical sense. It's mediated by particles. In quantum electrodynamics, which is the quantum theory of electricity and magnetism, forces are carried by photons, these little packets of electromagnetic field. When two electrons repel each other, they're actually exchanging virtual photons back and forth. The photons are carrying momentum from one electron to the other, and that's what creates the push. It's like if you and I were standing on ice and I threw a ball to you. When you caught it, you'd be pushed backward, and if you threw it back to me, I'd be pushed backward. We'd repel each other by exchanging the ball. That's kind of what electrons do with photons, except the photons are virtual, meaning they're quantum fluctuations that exist for such a short time that you can never detect them directly. But they're real in the sense that they create real forces. So when you push on a wall, what's really happening is that the electrons in your hand are exchanging vast numbers of virtual photons with the electrons in the wall, and those photons are carrying momentum that pushes you back. It's a quantum field theory picture of the world. There are no solid objects, just fields and particles and interactions. Now, I know this is a lot to take in. It's weird. It's not the way we experience the world in everyday life, but that's because our everyday experience is an average over huge numbers of particles and interactions. When you zoom in, when you look at what's really happening at the smallest scales, the world is quantum and strange and beautiful. And the thing is, this is not just philosophy. This is not just me sitting here spinning stories. We've tested these ideas. We've done experiments. Quantum mechanics makes predictions, incredibly precise predictions, and they match reality to an absurd number of decimal places. Quantum electrodynamics, the theory I was just talking about, is the most accurately tested theory in all of science. We can calculate things like the magnetic moment of the electron, and the theory agrees with experiment to something like 10 significant figures. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. So when I tell you that you can't walk through a wall because of the Pauli Exclusion Principle and electric forces mediated by virtual photons, I'm not guessing. I'm telling you what the universe actually does, as far as we can tell from every experiment we've ever done. And yet with all that precision, with all that success, there's still mystery. We still don't really know why the universe is quantum. We don't know why particles obey the rules they do. We can describe the rules, we can write down the equations, we can make predictions, but we don't have a deeper explanation for why those equations and not some other equations. Why does the Pauli Exclusion Principle exist? We can derive it from more fundamental principles in quantum field theory. We can show that it follows from the requirement that the wave function for identical fermions is antisymmetric under particle exchange. But why is it antisymmetric? Why are there fermions and bosons? Why is the world quantum at all instead of classical? Nobody knows. And maybe those questions don't have answers. Maybe at some level the universe just is the way it is, and we have to accept it. Or maybe there's a deeper theory waiting to be discovered, some more fundamental framework that will make everything click into place. But until then, we have quantum mechanics, and quantum mechanics says you can't walk through walls because the electrons won't let you. They push back with electric forces. They obey the Pauli principle. They form wave functions that don't have significant amplitude for you being on the other side. And that, my friends, is the answer. It's not because matter is solid. It's because nature has rules, deep quantum mechanical rules, and those rules make the world behave the way it does. Once you understand those rules, once you really see how they work, the world stops being a collection of solid things and starts being a dance of particles and fields and probabilities. And to me, that's more wonderful than any simple answer could ever be.